Hey, 1.4, sketching graphs of functions. So if you remember key points of the parent function, a less tedious method used to graph a function is to use mapping notation. And this is what we're going to focus on for this entire lesson and pretty much most of this course. Okay, so this rolls in from last year. So let's talk about transformations. So what are transformations? So the following is an equation for all possible transformations of the function y equals f at x. Okay, so whatever function you have, it doesn't matter if it's a sine function, a cos function, an x squared function, an x cubed function, a square root function. Okay, it doesn't matter if it's exponential, so like 2 to the x function. You can take all of these functions and the positioning of these values, a, k, h, and c, are all going to mean the same thing despite what function we're talking about. Okay, so if we have a number in this position here under a, okay, and this is in front of the function, so the function would essentially be like where this f is to this big box bracket. So if we had a number in here, this is going to be one of three things, or even two of three things. So it's either going to be a vertical stretch or a vertical compression. And if it's negative, it's going to be a reflection in the x-axis. So if that number, the absolute value of that number, so not including the plus or minus sign in front of it, but just the actual numeric part of it, if it's greater than 1, then our function is vertically stretched by a factor of a. And if it's between 0 and 1, so I call this a fraction, then our function is vertically compressed by a factor of a. I put fraction in quotation marks because if a is like, for example, 5 over 2, which is actually 2.5, then that doesn't hold. When we say fraction, we kind of mean like 0 decimal something. Okay, so quote unquote fraction. And then finally, if that number a is negative, right, less than 0, then our function is reflected in the x-axis. Okay. Next one, k. So if inside of the function we have a number beside x, that's going to be one or two of the following three things. So it's going to be either a horizontal stretch or horizontal compression. And then also it's going to be, if it's negative, it's going to be a reflection in the y-axis. So if the numeric part, so the absolute value of k, so just looking at the number portion, if it's between 0 and 1, quote unquote a fraction, right? Then what we actually have is our function is horizontally stretched by a factor of k. But it's by a factor of the reciprocal. So 1 over anything, if you remember, this is the reciprocal. So if this is, for example, 1 over 2, then we're stretched by 2. And that's why we have 1 over k there, because it's like a stretch by the reciprocal of that. Okay, if this number k, so the absolute value of k is greater than 1, then it is a horizontal compression by a factor of 1 over k. So whatever that number is, flip it. Okay, and then if k is less than 0, in other words negative, our function is reflected in the y-axis. Okay, the next one, h. So I want to highlight this. There is a built-in negative sign here. So whatever the h looks like, it's actually opposite. So let's talk about the h. What's going on with h? So if we have a number, so like x minus or x plus, this number in brackets, what this is going to do is this h value is going to horizontally shift left or right. Okay, I want to talk about this built-in negative sign. So if h is greater than 0, so in other words, if the h value is actually positive, I'm going to give you an example, h is positive 5. Then in that bracket, because the actual equation is x minus h, what happens is it actually looks negative. So this looks negative, but the h value is actually positive. Okay, then what happens is our function is translated or shifted h units to the right. And if the actual h value is negative, right? So let's scroll down here a little bit. Let's do example, h is -3. When we actually sub in the -3, what happens is it looks positive. So if h is less than 0, so it's negative, but it looks positive, then our function is translated h units to the left. So this one is backward to what you would think it would be, like considering the look of it. Okay. And now C. So after the function, if we have like a plus or a minus and a number, what this means is a vertical shift up or down. So if C is greater than 0, obviously that's a positive number. It's a vertical shift C units up. And if C is less than 0, so a negative number, it's vertically shifted C units down. Okay, so keep this handy while we're doing the questions. This is your complete overview of all of the transformations. Okay, so transformations must be applied in the following order of operations. So essentially, we need to apply them in the order of bed mass. So stretches, compressions, and reflections are all multiplication or division. So you have to apply those ones first. And then if we have any shifts, either vertical or horizontal, doesn't matter. This is addition and subtraction, so you apply those afterward. Okay. Keep this handy as well. This is our actual mapping notation and how we would apply this mapping. This is an H. Let's change that. So example 1, I'm going to do an example of a linear function. So usually in grade 9, we learn linear functions as y equals mx plus b, and we plot the y-intercept, and then we apply the slope. I'm going to show you what the equation of a line is when it pertains to applying mapping notation. Okay, so graph f at x equals x using a table of values. So this is going to be f at x equals x. F at x equals x or y equals x, you can think of it as this is our basic line that has no transformations on it. There we go. Okay, so if we were to graph x as -2, -1, 0, 1, 2, the y would also be the same because like it's y equals x or x equals y. So -2, -1, 0, 1, 2. Okay, and this is how the graph would look. Oops, that's x. Okay, now the domain and the range for this one, for any line, it's always xer and then yer. It's going to extend into the x direction and the y direction infinitely. Okay, now what about for the equation f at x equals 2x minus 3? So let's talk about the actual transformations that are being applied to this. Okay, and I'm going to leave this because I want to do the next chart right beside, and I want to do the domain and range underneath as well. Okay, so I'm going to leave this, I'm going to work over here. So this 2, this is in the A position. So this is a vertical stretch by a factor of 2. Okay, then we have this -3. So what position is that in? That's in the C position. So we have, we can do vertical shift or translation, 3 units down. So that's what's going on in 2x minus 3. So when we go from x to 2x minus 3, those are the two transformations that have to be applied. Okay, now let's talk about determining the mapping notation. Okay, so for mapping notation, we're going to take the original, which is xy over here, and we're going to talk about, okay, what's affected? Is the x affected or is the y affected? So in this one, neither of these affect the x. These are both vertical. Okay, so the x is going to stay the same. Now, when we stretch something by a factor of 2, that's in the A position. So we would have 2y, and then it's down 3 units, which is plus c, so it's -3. So this is going to be 2y minus 3. So what we have to do, so this right here, x comma 2y minus 3, that's fine for your mapping. You can put that right into a chart. Okay, so that's the mapping. Now the coordinates of the transform function. What we're going to do is we're going to take all of these x values and we're just going to duplicate them because it doesn't change. So -2, -1, 0, 1, 2. However, the y's are going to change. We're going to take all of these y's and we're going to sub them into 2y minus 3. So 2 times -2 is -4 minus 3, I get -7. So 2 times -1 is -2 minus 3, I get -5. 0 times 2, which is 0, minus 3 is -3. 1 times 2 is 2, minus 3, I get -1. And 2 times 2 is 4, minus 3, I get 1. And then with these coordinates, we can go ahead and we can graph our transform function. That's so bad. Okay, and that's going to be f at x equals 2x minus 3. Okay. And for the domain and the range, like for part B5, xer and yer stay because that is the domain and the range for any line. Okay, example 2, quadratic functions. So first, A, graph f at x equals x squared using the table of values and then state the domain and range. So let's do a table of values, x and y, and we could do -2, -1, 0, 1, 2. Okay, so -2 squared is 4, -1 squared is 1, 0, 1 squared is 1, 2 squared is 4. Okay, so for the domain of a quadratic function, and the quadratic is going to look like this. Okay, so the domain is always going to be XER no matter what. And the range, we have to take a look at where the vertex is. Okay, the vertex is 0, 0. So we use the y coordinate of the vertex. So YER such that y is greater than or equal to 0. And the greater than or equal to sign comes from whether it opens up or down. Okay, so it's greater than if it opens up, and it's less than if it opens down. And this y is the y of the vertex. Okay, so that's the rule. Now let's take a look at our new function. F at x equals negative 3x squared plus 5. Okay, so if we line this up with y equals negative 3x squared plus 5, we can see that we have an a value of negative 3. Our function with like the x just stays as x squared, so there's no transformation on the x. And then the c value is 5. So looking up in our chart, what's happening with the a? So if it's negative, it's reflection in the x-axis. And it's a 3, so it's a vertical stretch by a factor of 3. Okay. And then we have C is 5, and if you look up the C, what's going on with C? It's either going to move up or down. So this is a vertical shift, or translation, whatever you want to call it. Shift up 5 units. Okay, so now let's determine the mapping notation. So we know that there is no k value and no h value. So our x comma y maps onto just x. And then if we look at ay plus c, our a value is negative 3, so negative 3y, and then our c value is plus 5. Okay, so all we have to do is we have to come up here, and we have to map all the x's onto x, which doesn't change. There's no transformation on the x values. And then we're going to take all of the y's and we're going to map it on to negative 3y plus 5. So every single y coordinate here has to be stretched by 3, reflected, and then moved up 5. So negative 3 times 4 is negative 12, plus 5 is negative 7. Negative 3 times 1 is negative 3, plus 5 is 2. Negative 3 times 0 is 0, plus 5 is 5. Negative 3 times 1, so that this will be symmetric, right? Because we have the symmetry with quadratics. So negative 3 times 1 is negative 3, plus 5 is 2, and then negative 3 times 4 is negative 12, plus 5 is negative 7. So let's go ahead and graph that. So negative 2 comma negative 7, negative 1 comma 2, 0 comma 5, 1 comma 2, 2 comma negative 7. Okay, and this is our graph of f at x equals negative 3x squared plus 5. Okay, domain never changes is XER. And when we talk about the vertex, if our vertex was 0, 0, and now our vertex after applying these transformations, 0, 5, like that's lateral, right? So if we apply these transformations onto the vertex, this is also going to be our vertex. So we're going to have YER such that we're going to compare Y with the Y coordinate of the vertex, okay? And we're going down. So Y is going to be less than or equal to 5 because we're kind of quote unquote starting at 5 and our graph is going down. Okay, example 3, exponential functions. So first we're going to graph f at x equals 2 to the x using a table of values. So I'm going to go f at x equals 2 to the x. I'm going to create a table of values that has -2, -1, 0, 1, 2. Okay, so 2 to the exponent -2 is 1 over 4. 2 to the exponent -1 is 1 over 2. 2 to the exponent 0 is 1. 2 to the exponent 1 is 2, and 2 to the exponent 2 is 4. Okay? Something special about the exponential function, there is a horizontal asymptote, and the original horizontal asymptote is at y equals 0. So this is y equals 0, and then we're going to graph this. So we have -2, comma, a quarter, -1, comma, a half, 0, comma, 1, 1, comma, oops. That's if this was, let's put this down more. Quarter, a half, 1, and 1, comma, 2. And I'm just going to extend this. This would be 1, and then this would be 2. And then 2, comma, 4. So that is going to look like this, and it's going to go up. Okay? Sorry about the graph. All right. Now, let's talk about domain and range. So, domain is going to be XER. That's for every single exponential function. And the range is going to be YER such that Y is greater than strictly 0. So, where do we get these numbers from? So, it's either going to be Y is greater than or Y is less than, depending on if your graph goes up or if it's reflected. So if there's a reflection in the x-axis, it's going to go down. Okay, it's going to be less than. And then this is our value from the horizontal asymptote. Okay, so it's just like a general rule right there. Now, let's take a look at the transform function. Okay, so we have f at x, I'm going to rewrite it over here, equals 3 times 2, so 3 times 2 to the power of 2x plus 4, and then plus 1. So remember, our function is 2 to the x, and 2 to the x is already taken into account in this chart. And remember, since it's 2 to the x, like this 2 is not a transformation. That is our base graph. So let's talk about the transformations. So this, let's go yellow. This 3 is our A value. So this is a vertical stretch by a factor of 3. Our function is the 2, so we leave it. Now let's look around the 2 and see what's going on, or sorry, around the x and see what's going on. So this is our K value. This is a horizontal compression by a factor of 1 over 2. Remember, the K, it's a compression or a stretch by that reciprocal. Our H value, it looks negative, so it's actually positive. So horizontal shift 4 units right. Right. It's backwards. It has that built-in negative sign. And then this is a vertical shift. 1 unit up. Sorry, my mistake. This was 4 units left because the H is -4. Right? Looks positive, but actually negative. So let's go ahead and let's take these and let's create the mapping for it. Okay, so I'm going to create the mapping straight into this what's called the table of values. So here are the questions. Do we have a K value? Oh, this is H. And then do we have an H value? Okay, so our K value is 2. So it's 1 over 2, right? 1 over K. So 1 over 2x. And then our H value is -4. We're going to the left 4. So -4. Now, AY plus C. So our A value is 3. So we have 3y. And then plus 1. Okay, and now what we're going to do is we're going to take every single value of x and we're going to sub it into, we're going to half it and then subtract 4. Okay, so what is a half of -2 minus 4? I get -5. I'm going to do this in purple. Okay, what's a half of -1 minus 4? I get -4.5. A half of 0 minus 4, I get -4. A half of 1 minus 4, I get -3.5. And a half of 2 minus 4, I get -3. Okay, and we'll write horizontal asymptote. Okay, now what we're going to do is we're going to take every single value of the y's and we're going to plug it into 3y plus 1. Okay, so what is 1/4 times 3 plus 1? I get 1.75. What is 1/2 times 3 plus 1? I get 2.5. 1 times 3 plus 1, I get 4. 2 times 3 plus 1, I get 7. And 4 times 3 plus 1, I get 13. Now, the horizontal asymptote, because this is a y value, we can sub in 0 for y and get our horizontal asymptote. So 3 times 0 plus 1 is going to give us a horizontal asymptote of 1. And then we can go ahead and we can sketch this. So horizontal asymptote of 1. So that's going to be y equals 1. And then we're going to go -5, comma 1.75. -4.5, comma 2.5. Okay, so we have -4 and 4, -3.5 and 7, -3 and 13. Put that over there more, and then 3 and 13. So now we have this function, and it looks like this. Okay, so this is f at x equals 2 to the x. This is our original. And then this is f at x equals 3 times 2 to the 2x plus 4 plus 1. Okay, now let's just talk about domain and range. So domain, range. Domain is XER no matter what. And range is going to be YER such that y is greater than the horizontal asymptote, which is 1. Okay, so example 4, we're going to do the square root function. So graph f at x equals the square root of x using a table of values and state the domain and range. Okay, so if we have f at x equals the square root of x, we're going to have a table of values in the form x comma y. And the numbers that we're going to use are 0, 1, 4, 9. Okay, if you take a look at all of these numbers, we can square root all of these numbers and get integer values. Okay, so the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So that's here, f at x equals square root of x. Now, in regards to the domain and range, what we're going to be looking at every single time is this first coordinate, so the one pertaining to 0, 0, okay? And when we transform that coordinate, we'll take a look at that, but this is the one that we're going to be always writing the domain and range in regards to, okay? So as long as the square root is opening the same way, we're just going to have x is greater than or equal to 0, and then y is greater than or equal to 0. And these will only change when we have, for example, a reflection like this, a reflection like this, or a reflection like this. Okay, and then all that's going to change is the inequality. Okay, now let's take a look at for the equation f at x equals 2 square root of negative 1/3 x plus 1. We are going to state the transformations of this one. And I'm sorry about the numbers there. So let's go ahead and say this 2 is a vertical stretch by a factor of 2. So let's put it down here. So vertical stretch by a factor of 2. So the negative and the 1/3 pertain to the k value. So the negative represents, from our chart, reflection in the y-axis. Okay, and the 1/3, remember this looks like it would be a compression because it looks like 1/3, but it's actually the opposite. So this is a horizontal stretch by a factor of 3. Okay, and then the plus 1 in the bracket with the x is going to represent, remember it looks like a plus sign, so it's actually left. So horizontal, shift, left. How many is that? 1 unit. Okay, if going through like that is a little bit too quick, what you want to do is you want to stack it with this equation and really line these up. So the 2 is clearly the a value, the k is negative 1/3, and the h is negative 1. So when we're doing the mapping notation, x comma y is going to map onto, so 1 over k, because this is a horizontal stretch, it's going to be like negative 3. So the negative is going to be the reflection, and the 3, because we're going to take 1 over k. Our k value is actually negative 1 over 3. So if we took this and we did 1 over negative 1 over 3, we know that 1 over anything is just the reciprocal. So all we do is we take this and we take the reciprocal of it. So of course, flip it, we get negative 3 over 1, aka negative 3. Okay, the x comes down. The h, we're going left 1 unit, so it's negative 1. And then ay plus c, the a is 2, so 2y, no c value. And we can take that mapping and we can translate it up here. So for every x value, we're going to multiply it by -3 and then subtract 1. And for every y value, we're going to multiply by 2. So we take all of these x values from the original and we sub it into here. So -3 times 0 minus 1, -3 times 1, which is -3 minus 1, which is -4. -3 times 4 is -12, minus 1 is -13. This is -27, so -28. And then we're going to double all the y's, okay? 0, 2, 4, 9. And go ahead and graph this. So -1, 0, -4, 2, -13, 4. And I am going to change this grid next time. Here we go. Okay, and then we label f at x equals to -1/3 x plus 1. Okay, now domain and range. Set it up, XER, YER, and we know that x is going to be something pertaining to this point, right? This is our reference point for domain and range. So the x value is -1 and the y value is 0. What we have to do is we have to take a look at our graph and be like, okay, what way is this opening? So the x values go to -infinity. So x is less than or equal to -1. And then the y's go up forever, so y is greater than or equal to 0. Okay, absolute value function. So first we're going to graph f at x equals the absolute value of x. Okay, so when we do this, we have x and we have y, and the numbers that we would use is -2, -1, 0, 1, 2. And then the y values are going to be all of these x values, just the positive ones. Okay? So when we go ahead and graph this, 0, 1, 2, 3, 4, 5, 6, beautiful. -1, 2, 3, 4, 5, sure. And I just did that by like, obviously, patterning. Okay? So let's talk about domain and range. Very similar to that of a quadratic. Okay, start with the XER, YER. What we want to do is this is not called a vertex. We only call it a vertex when we're doing quadratics. However, that's going to be our reference point where like it would be comparable to the vertex on a quadratic. So we're going to go x is greater than or equal to 0 and y is greater than or equal to 0. No, I'm lying. XER. What am I doing? Sorry, y is greater than or equal to 0. So XER, because it's going to go to -infinity and it's going to go into infinity. And then the y's go up forever, right? 1, 2, 3, 4, 5, 6, and up forever. Now, I'm gonna write this down here. I like when I do that. -3, 1/2 x minus 3. So we're gonna have y equals -3 absolute value. I think it's -1/2 x minus 3. I'm so guessing this. Hold on a second. Oh, it's +1/2. Okay, cool. X minus 3. All right. So the f is our function, and that is these two bars, absolute value. And again, from before, we took into account this f, this function, when we graphed the original here, okay? So let's write our mapping notation. Oh no, let's first state the transformations. So on the a value, we can do this all together. On the a value, there's a negative and a 3. So this is a reflection in the x-axis. This is also a vertical stretch by a factor of 3. Okay. For the k value, it looks like 1/2, but we have to take the reciprocal. So it's 2. This is a horizontal stretch by a factor of 2. Now, this looks like a -3, but we know that there's the negative built in to the equation. So it's actually +3. So we're going to go horizontal, shift, 3 units right. Okay, no C value. So now when we're taking a look at mapping notation, x comma y is going to map, so 1 over k, so our k value is 1/2, so we get 2x, did it again, this is an h, plus h. H is +3, right? 3 units right. Remember, this looks negative because there's a built-in negative sign. Then we have ay, and we don't have a c for this one. So -3y. So let's come back up here, and we're going to go 2x plus 3, -3y. Sub all of these x's into 2x plus 3. So -4 plus 3, -2 plus 3, 0 plus 3, 2 plus 3, and then 4 plus 3. Okay, take all of these y's and sub them in, multiply them by -3. So 2 times -3, 1 times -3, 0 times -3, 1, and then 2. And we can go ahead and graph this as our transform function. So -1 comma -6, 1 comma -3, 3 comma 0, 5 comma -3, 7 comma -6. Okay, and this is y, or f at x, equals -3 absolute value 1/2 x minus 3, right there. Okay, so when we set up the domain and range, we want to do XER, YER. So very similar to a quadratic, XER always stays, right? We're going to go in the left and right directions forever. And for the Y, we're going to look at this reference point, 3, 0. But we're looking at the 0 for the Y. And because there's a reflection, we're actually going down now. So Y is less than or equal to 0. Example 6, cubic function. So we're going to graph f at x equals x cubed using a table of values and then state the domain and range. So f at x equals x cubed. We're going to have x and y. We're going to have -2, -1, 0, 1, 2. And we're going to go -8, -1, 0, 1, 8. I think that's correct. 1, 1, 2, 8. Yes, it's going to go like this. Beautiful. And then -1, 1. And then -2, 8. Awesome. Amazing. Here we go. X cubed. Okay. Now, state and words transformations. Okay, I'm going to copy this down here. So -3, 2 minus 2 plus 5. Okay, so I'm going to have -3, 2, and then x plus 2. I said it's -5 plus 5. And I'm going to just double check that. -3, 2, -2. Oh, this is a -2. Okay, and then the function, which is here, would be cubed. All right, let's talk about these. So the a value has a -3 on it. So this is reflection in the x-axis. And the 3 means vertical stretch by a factor of 3. Okay, this k value is 2, so it's actually 1 over k we're thinking of, so it's a horizontal compression. By a factor of 1 over 2. Okay, this h value, so see how this negative sign is built in and this negative here? So h is directly 2. Okay, so this is horizontal shift. 2 units right. Then we have 5 for the C, so this is a vertical shift. 5 units up. Okay, so now let's take a look at the mapping notation. So x comma y maps onto, so it's going to be 1 over kx plus h. So our k value is 2, so this is 1 over 2x plus h, so plus 2, comma, negative 3y plus 5. So let's transfer this up here. 1 over 2x plus 2, negative 3y plus 5. And let's go ahead and sub in these x's to here. So half of negative 2 plus 2, negative 2 times 0.5 plus 2 is 1. Okay, negative 1 times 0.5 plus 2 is 1.5. Then we have 2. Then we have 2.5 and 3. Okay, easy. Then the y's, multiply all the y's by negative 3 and then add 5. So I get 29, 11, 5, 2, negative 19. Okay, let's go ahead and graph this. 1 comma 29, 1.5 comma 11, 2 comma 5, 2.5 comma 2, 3 comma negative 19. So that is our transform graph. F at x equals negative 3 to x minus 2 cubed plus 5. Okay, and don't forget the domain and range. Domain and range for cubic function is similar to a line. It's going to be xer, yer, no matter what. Put that on your short form sheet, xer, yer. Okay, it's going to extend into the x direction forever, and then the y direction forever. Sorry, correction, this is 8. So 1.5, it'll be just a little bit more down, 8. Okay, reciprocal function. Graph f at x equals 1 over x. It is a unique one, and then we're going to state domain and range. So for the x and the y, I only need 2 coordinates. I need the -1 and the 1. That's it. So -1, 1, 1. Here's the thing though. There is going to be a horizontal and a vertical asymptote. Okay, the horizontal asymptote is going to be at y equals 0, and the vertical asymptote is going to be at x equals 0. Okay, so -1 comma -1 is plotted here. This point will be in one of the quadrants, like the quadrants divided by the horizontal and the vertical asymptote. The other one, 1, 1, is going to be kitty corner to it. So it's going to be diagonal to it. It will never be beside each other, okay? Not for the scope of the 1 over x function. And then you can simply draw curves approaching the x-axis and approaching the y-axis. Okay, and how would we set up the domain and range? Well, of course, set up the xer, yer. And then this is the rule. X does not equal, and if you think about the x coordinates, -5, -4, -3, -2, -1, oh, x does not equal 0. Let me erase that. Okay, which is going to be the vertical asymptote. So that's like a general form. X does not equal the vertical asymptote, and y does not equal the horizontal asymptote. Okay, so now let's go ahead and write this down here. 1 over x minus 3 plus 5. Okay. Oh, this is a little bit more complicated. Let's get deeper. 1 over x minus 3 plus 5. Okay, here we go. So this is a 1 over x function. There's no a value in front, so don't worry about that. Now the function itself is 1 over x. There's nothing multiplied by the x, so don't worry about the k. We are going to focus on x minus h and then the plus c. So because it's x minus 3, our h value is 3, right? Because again, negative is built into this equation. So this is going to be a horizontal shift, right 3 units. Then the plus 5 is going to be vertical shift, up 5 units. So our mapping notation is going to map all of the x's, we're going to add 3, and all of the y's, we're going to add 5. So let's take the x plus 3, y plus 5, and we will go here, x plus 3, y plus 5. Okay, so -1 plus 3 is 2, 1 plus 3 is 4. -1 plus 5 is 4, 1 plus 5 is 6. And we have horizontal asymptote, vertical asymptote, y equals, x equals. Okay, now here's the thing. See how y equals 0? So for the horizontal asymptote, we're just subbing the 0 into the y value. We get 5. So what that will mean is we're going to have a horizontal asymptote at y equals 5. Okay, and the vertical asymptote is x equals 0. Sub it in here, x equals 3. Okay, so when we go ahead and plot 2, 4, we can see that it's in this quadrant. And 4, 6 is going to be in the opposite quadrant, and then you can just draw a curve. So you really only need like the reference point of like where it lands, and it's always opposite to one another. Okay. Okay, and now let's set up our domain and range. So it's always going to be xer such that x does not equal, yer such that y does not equal. So again, logically, x equals -5, all these numbers -4, all these numbers -3, -2, -1, 0, 1, 2. Oh, x does not equal 3, which is our vertical asymptote. Then if we look at the y coordinates, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. Oh, we get to 5. Our graph never hits 5. So the range, y does not equal 5. And that's it.